Good morning. See, in safety critical industries like nuclear industry, you are very always scared of software because if there is software in it, you are scared whether there is a bug in it. And in nuclear power plants, whether you like it or not, like in any other field, software is embedding. The pretty good old transmitters, whose job is that to sense the process signals, be it a pressure, temperature, okay, they convert it to 4 to 20 milliamp per signal. For safety critical system, that much is good enough. You want to have a 4 to 20 milliamp per signal. But since nowadays we don't get the good old conventional analog electronic transmitters, they have become smart. That is, they have software inside it. So there is a worry that how do we use this transmitter in nuclear industry with confidence. Because in a power plant, typically there are thousands of analog signals which needs transmitters. So is there any way to validate and have confidence on it because it contains a pre-developed software? I'll just quickly go to what is a transmitter, because it is basically a transformer. It reads the input signals, temperature, pressure, as I already told, and then convert it to 4 to 20 milliamp per signal. Now, when you add smartness to it, we can change it configuration online. We have the communication facility, and we can save data online also. So this is good features for conventional industry, but this is also good for nuclear industry, but it is not essential. But since it is there, we have to look into it. So just this is a generic transmitter model as per IEC 60770 part 3. So here we are worried about these data processing subsystems, because anyway these are conventional electronics, human interface domain, there are buttons, then communication interface. For a safety critical system, we can even do away with the communication. You don't need communication. Our priority is safety. Okay, there is electrical output system, there is again electronic system. Now the problem is that earlier good old transmitter, analog transmitters, we would do just accuracy related performance testing, that would have been enough. But now since there is a software, so if there is a pre-developed software, there are guidelines how to qualify it, provided we get their software development lifecycle documentations, or if they do not have that SDLC documentations, we can take the source code and have confidence. You can check and do all sort of testing from outside. And since we have the confidence of the, is a long time usage of the analog electronics that we had the confidence to use it. But these smart transmitter softwares, it is we really don't have the confidence. So, and if you ask the vendor that do the verification and give a qualified transmitter for us, so they will not do for if you buy for a small amount. And also another factor is that there are embargoes. Even for India, say a US company will not supply that transmitter. They will be prohibited to sell it, even they have a qualified transmitter. So can validation be an option? By testing, can we really prove that, okay, this transmitter is useful, means useful, is qualified for use in safety critical system? So this is all very known that testing it says that it can say that the presence of bugs, but it doesn't guarantee the absence of bug, because 100% testing is not possible. Now, but still there is a hope, because if it is a very simple system, people are very paranoid with that software means there can be a bug. But for a simple system, which is a single input and single output system, can you really do something for it? Okay, so what we are claiming with that, for a single input, single output system, the test space can still be finite, and you can do exhaustive testing. So what is there in that, we have that block diagram. Now what is there in that transmitter is that there is a analog to digital conversion unit, which basically gives signal to the microcomputer. Now ADC has its own limitations, because it cannot detect any signal which comes within its resolution. That is, if it is a 12-bit ADC, okay, it has a limitation of 2 raised to 12, that is 4096, that is the resolution band. So it cannot really differentiate between the inputs between 2 digits. So other things, what we have is that, see, in microcomputer there are many configuration data those are typically constant data. And even if they have their filtering algorithm or linearization table, those are again constant. So even if we do for formal verification for any software, what you basically check is that there are certain variables as the program goes on executing, how the inputs are changing, is it going to land up in a situation which is unsafe. But if your input state is, if your input states are exhaustive, then we can guarantee that it will cover all the software states, and there will be no path which will not be covered, and we can say that I have tested everything of the software. So as I told, that ADC cannot detect between two consecutive discrete inputs as different ones if it is required to step differences delta. That is, if the high value minus low value and it divided by n minus 1, and is that what is the resolution of the transmitter, it cannot detect it. So there is no point in increasing the number of input space. And configuration data, they are constant. Range values, 0, span values is constant. Engineering conversion is constant. Filtering is constant. Linearization techniques may be different for different transmitter, but it is a constant table. So as I said, that a software state can change. It can change by external or internal events. So what are the possible external events? Updating the software input. There is a test button. There is triggered by the operator, or that communication request. Now this communication part, it has got a large communication, large chunk of software which implements the HART protocol, mostly in transmitters. So as I told in the earlier, that we can do away with the communication. We can physically remove the communication cable, and we can say that this software is not using any time. And internally there is a valid input, there is a clock tick, and self-diagnostics, there is a periodic tree. Now I'm not claiming that this is the state chart for all that. This is the detailed tester for any transmitter, but this is the first level state charts what you have studied from all the commercial transmitters, this Endres Hauser, Rosemount, Yokogawa, all these transmitters. This is the very first level. No transmitter beyond this if it has followed IC 60700 part 3 standard. So it has to read the input, it has to process the input, it has to send the output. And we have the parallel states of communication. Then we have a diagnostics, that is the online diagnostics. Okay, so that is anyway being checked because periodically it is being processed. So every time for all the inputs it is being checked. And there is an event test button is there, that is outside the scope. In all the transmitters, if you see the test, this is the state chart. See, when it is in the test mode, the transmitter is really not working. It is neither acquiring input nor sending any output data. It is working with the old data. So as I told, that we can do the communication. So once we debug communication physically, okay, and once we have that configuration data constant, then if we check for all the inputs to the extent to the resolution of the ADC, then we can claim that we have checked all the software paths for all possible variation in the input space. So what you have a test setup, this is a very simple setup. We did for a temperature transmitter. So temperature simulator, there are very good temperature simulators by Fluke and many other companies. So inject that temperature, that is we can inject for RTD, we can inject very precise ohm values. For thermocouple, we can give millivolt values. Then communication device, this is used for one time only, because initial configuration, whatever we say that transmitter has the upper range value, there is a lower range value. Okay, the filter type we use, that we can do it once, then we debug the communication. So we can certify that this transmitter for that particular configuration data, this will be validated. Now this temperature transmitter, it goes to the digital recorder, and the precise station we can see that digital recorder. If there is any problem, it will be recorded. So we have seen that. Now if you do a little bit calculation, that for a 12-bit ADC, the resolution is 1/4096, that is 0.09. And we have this test data is an excerpt of state data for all the 4096, rather double for the 2 multiplied by 4096, because we wanted to check the in-built value of the data. So we had gone for 0.05 resolution, okay, instead of 0.09. And what you observe that the transmitter is really able to make a change in any difference till that value changes to 0.25. Okay, and it detects a change when there is a change in the point more than 0.25, and this is the 4 to 20 milliampere output. So that is 20 minus 4 by 4096 that comes, and that again depends on the what is the precision of the output measurement. So we find that we do not really need to check for these type of inputs. So that makes our, see, if we check here and here and here, that saves our process. So we can save all this in between inputs. So this is not required. So that makes our input state space finite. So this is a typical graph for a complete range. We found there is no glitch. There is no undesirable output, and our safety property is that it should not go to an undesirable value. So the conclusion is that exhaustive testing is feasible for a single input, single output device like smart temperature transmitter, and same principle can be applied for the pressure and level transmitter also. And this can be automated because nowadays we have a good flow transmitter switcher from the PC. You can automatically generate that inputs. Transmitter also have a settling time, so you can give input only after 200 milliseconds, even if the fastest transmitter we use. So it can be automated, and a single transmitter can be validated in a span of half an hour. So this is still feasible when we are trying to use transmitter for safety critical applications. Thank you.